As far as the laws of mathematics refer to reality, they are not certain. And as far as they are certain, they do not refer to reality, said by Albert Einstein. If people do not believe that mathematics is simple, it is only because they do not realize how complicated life is, said by John von Neumann. Good afternoon, everyone. We'll start our webinar with Tamil Thai வாழ்த்து, followed by a prayer song.
நீராறும் கடலொடுத்த நிலமடந்து எழிலொழுகும் சீராரும் வதனமென திகழ்வரத கண்டமீதி எக்கணமும் அதிசிறந்த திராவிடனல் திருநாடும் தக்க சிறு பிறை முதலும் தரித்தனரும் திலகமுமே அத்திலக வாசனை போல் அனைத்துலகும் இன்பமுற எத்திசையும் புகழ் மணக்க இருந்த பெரும் தமிழனங்கே தமிழனங்கே உன் சீரிழமை திறம் மிகுந்து செயல் மறந்து வாழ்த்துதுமே வாழ்த்துதுமே வாழ்த்துதுமே.
सत्यव्रतं सत्यपरं त्रिसत्यं सत्यस्य योनिं निहितं च सत्ये सत्यस्य सत्यं ऋतसत्यनेत्रं सत्यात्मकं त्वां शरणं प्रपन्नाः वाणी गुणानुकथने श्रवणो कथायां हस्तौ च कर्मसु मनस्तव पादयोर्नः स्मृत्यां शिरस्तव निवास जगत्प्रणामे दृष्टिः सतां दर्शनेस्तु भवत्तनूनाम् नमो भगवते तस्मै कृष्णायाद्भुतकर्मणे रूपनामविभेदेन जगत्क्रीडति यो यतः ॐ शान्ति शान्ति शान्ति.
Feedback link will be posted in the chat box at the end of the session. Now I request Ms. C.M. Subbulakshmi, Assistant Professor, Department of Mathematics with Computer Application, to deliver the welcome speech and introduce our resource person.
A very good afternoon to one and all. It is my privilege to give this welcome address and introduce our speaker for the day on behalf of Department of Mathematics with Computer Application. I welcome all our participants and faculty members for this today's webinar. It is my honor to introduce our speaker, Dr. S. Sunil Verma, who has completed his undergraduate program in the year 2000 under the University of Madras and did his postgraduate in the Indian Institute of Technology and completed his PhD program under the guidance of Dr. Rosie Thomas. His area of specialization is univalent functions and univalent function and harmonic univalent. He started his career in an engineering college and has experience of about 9 years, and he has joined the MCC college in the year 2011. He has also qualified CSIR NET and GATE in mathematics. He has also completed UGC minor project Radius Problems for Subclasses of Analytic and Harmonic Univalent Functions. He has also published over 25 papers and presented 10 papers in national and international conference. It is a pleasure listening to you, sir. I request our speaker to take over the session.
Thank you, Subbulakshmi madam.
Thank you, sir.
Respected head of the department, Department of Mathematics and with Computer Applications, DG Vaishnav College, faculty members of the department, students, and viewers of this program. Uh, I thank you for giving this opportunity. I was asked to talk on complex and basic complex analysis. I think this is intended to third UG students who will be doing the course in the next semester. So I have set my talk in such a way that it's very elementary, and so that people students who are yet to do a course in complex analysis can understand. Is my screen visible? Am I screen visible? Yes. Okay. Is my screen visible? Hello. Am I audible? Okay. Hello. Okay. So the outline of the talk is as follows. So, what is complex analysis? History of complex analysis. Why should one learn complex analysis? Real number system and their properties. Because before going to complex number system, we have to look at a real number system. Complex number system and their properties. Topology of the complex plane. Complex valued functions of complex variables. Limits, continuity, and derivative of complex valued functions. And finally, we will stop with what is known as analytic functions. What is complex analysis? According to Wikipedia, complex analysis, which is traditionally known as the theory of functions of a complex variable, is a branch of mathematical analysis that investigates functions of complex numbers. It is helpful in many branches of mathematics, including algebraic geometry, number theory, analytic combinatorics, applied mathematics, in physics, and so on. So, complex analysis basically deals with the functions of complex numbers whose values are also complex numbers. If you look at the history of complex analysis, it has its roots in the 18th century and just before prior. Important mathematicians like Euler, Gauss, Riemann, Cauchy, Weierstrass are connected with this field of mathematics. This also is a source from Wikipedia. Complex analysis mainly deals with complex valued functions of a complex variable. I am reiterating this. Now, why should one learn complex analysis? One reason is for its aesthetic beauty of results. So, like any other field in mathematics, it is beautiful with elegant results on its own. It has very deep results, which are also used in other areas. There are also several branches of complex analysis. And for applied mathematicians, engineers, and physicists, there are profound applications of complex analysis in their own area. It is very useful in solving differential equations because if you look at the partial differential equation, if you look at an analytic function, the real and imaginary part are essentially parts satisfy harmonic Laplace equation, or they are harmonic. Real and imaginary part are harmonic, which turns out that is the real and imaginary part satisfy partial differential equation, which is called the Laplace equation. And this Laplace equation arises in many areas of physics like electrostatics, fluid dynamics, heat conduction problem, etc. Other than this, tools of complex analysis are used in solving differential equations like using Fourier and Laplace transform. So when you are given an ordinary differential equation and when you apply the technique of Laplace transform or Fourier to solve it, we will be ending up with a function in a new variable, which is essentially a complex variable. And inverting that function will give the solution of the differential equation. And to invert, the techniques of complex analysis are used because those functions will not be free from singularities. So we have to tackle in such a way that we are able to find the residues at those singularities and try to use something like Cauchy residue theorem. In mathematics, if you look at the problem of evaluating the integral 0 to infinity dx by 1 plus x power n, it is really tough. Of course, you can evaluate 0 to infinity dx by 1 plus x, dx by 1 plus x square, 1 plus x cube, and 1 plus x power 4. In fact, dx by 1 plus x cube and dx by 1 plus x power 4 itself is very tedious because it involves factorizing the denominator and applying partial fraction. But complex analysis will come to our rescue. You can use the methods of complex analysis, especially contour integration and thereby Cauchy residue theorem, and you can evaluate such integrals no matter what is the power n. And also complex analysis is used in algebraic geometry, number theory, etc. Let us now recall the real number system and their basic properties. And from this, we will try to switch over to complex number system, and let us see what and all are preserved and how much it differs from real number system. The set of real numbers R is a field under two operations, namely addition and multiplication. This is well known in your UG second year in algebra course. You would have proved this is a field. But apart from addition and multiplication, R also has or is gifted with what is called order relation, namely less than among the real numbers. That is, given any two real numbers a and b, either a will be less than b or b will be less than a. This is well known. And that is why geometrically the real numbers form a straight line. You can plot, you can identify any real number on a straight line, and vice versa. Any point as a point in a straight line, and vice versa. And this order relation is a partial order relation, plus it is also totally ordered, given because for any xy, either x will be less than y or y will be less than x. So the relation, order relation mentioned here as the following property satisfies the following axioms. Exactly one of the relations x equal to y, x less than y, or x greater than y holds. X greater than y is same as y less than x. If x less than y, then for every z, we have x plus z less than y plus z. If x is positive and y is positive, then their product x into y is also positive. If x is greater than y and y is greater than z, then x is greater than z, transitivity. So these are the axioms which the order relation of real numbers will satisfy. And we characterize real numbers like positive real number and negative number based on x greater than 0 or x less than 0. Also, if x is less than y and z is positive, then x is z less than y is z. If x is less than y and z is negative, then x is z greater than y is z. And if x is greater than y and z is greater than w, where both y and w are positive, then x is z greater than y w. In real number systems, x less than or equal to y means either x strictly less than y or x equal to y. Similarly, x greater than or equal to y means x greater than y or x equal to y. And if x greater than or equal to 0 or x less than or equal to 0, then x square is greater than or equal to 0. We know that square of a real number is always non-negative. If it is 0, it is 0. Otherwise, it is strictly positive. And this is the key point for us also, because square of a real number is always non-negative. Now, need for extending the real number system to complex numbers. We all know about real numbers. We know that it is a field. We have studied about functions of real numbers. We have solved equations with the real coefficients in real variables, etc. But still, why should we go for complex numbers? In this slide, I told that if x is real and if it is either negative or positive, then x square is greater than or equal to 0. Now, look at the situation. Consider the elementary quadratic equation x square equal to minus 1 or x square plus 1 equal to 0. If you search for a real number which satisfies this equation, you cannot find one, because just now I mentioned that square of a real number is always non-negative. It cannot be negative. Hence, we go for new types of numbers called complex numbers in order to find a solution for this equation. So, new types of numbers called complex numbers have been introduced to provide solution to such equation. How do we do that? We assume that there is a solution denoted by I to this equation. meaning I is a number. It cannot be real for sure, such that I square equal to minus 1. So we make this assumption and we give a name to this I as imaginary unit, so that I square is minus 1 or equivalently I equal to root minus 1. So for convenience, we say that the symbol I, which takes the value root minus 1, is a solution for the equation above. The symbol was introduced by Euler in the year 1748. Now we can form the set of complex numbers. Set of complex numbers looks like it consists of all numbers of the form a plus ib, where a and b are real, and I equal to root minus 1. From basic algebra, we know that it is also a field under the operations shown here. A1 plus IB1 plus A2 plus IB2 equals A1 plus A2 plus I times B1 plus B2, and A1 plus IB1 multiplied by A2 plus IB2 equals A1 A2 minus B1 B2 plus I times A1 B2 plus B1 A2, where the operation in the bracket is product and the difference between real numbers. Now, so under these operations, set of complex numbers forms a field. We know that pretty well, and it is also isomorphic to R2. R2, where R2 is a set of all ordered pairs A comma B, where A and B are real numbers. Now, once you have the complex numbers, the complex numbers will provide solutions to general algebraic equations of the form A0 plus A1x plus etc. plus an x bar n equal to 0, where A0, A1, etc. an are arbitrary real numbers. In fact, that's one fundamental theorem of algebra. Now, we saw an order relation in set of real numbers. Can we extend the order relation, the same order relation, to set of complex numbers is the question. It is impossible to give a definition of less than for complex numbers, that is order relation for complex numbers, which will have the properties mentioned above for real numbers. You may remember that I mentioned nearly 4 or 5 axioms which the order relation on R, real set of real numbers, should satisfy. But if at all you are extending this order to complex numbers, then those properties should be preserved. But it is impossible. Let us see why. To illustrate this, suppose you have a total ordering on C. You have that is given any two complex numbers, say Z and W, either Z less than W or W less than Z. Now we know that I is an element in C, where I is root minus 1, and it is not equal to 0. It's not equal to 0. Then by the axiom 1, which I stated earlier, meaning, yeah, exactly either x equal to y or x less than y or y x greater than y holds. Using this axiom, we can tell that either I less, because it is not equal to 1, it should be either positive or negative. I should be either greater than 0 or I should be less than 0, using that property. Assume that I is positive. Then by axiom 3, right, that is whenever x greater than 0, y, x is greater than y is it, we can prove, we see that I square greater than 0. That is, you write I greater than 0 2 times. I greater than 0, I greater than 0, then I into I greater than 0 into 0. Okay, so I square greater than 0. But what is I square minus 1? So we end up with minus 1 greater than 0, which is not true, we know. Let us proceed further. Add 1 on both sides. We get 0 greater than 1. 0 greater than 1. Now I apply axiom 3 to minus 1 greater than 0. So minus 1 into minus 1 greater than 0 into 0, which gives 1 greater than 0. So we find that 0 is greater than 1 as well as 1 is greater than 0, which is impossible by axiom 1, because given any two numbers x and y, say complex numbers, either it should be x greater than y or y greater than x. Both cannot happen simultaneously. Hence, this is impossible. This impossibility came because we assumed the order relation is true for complex numbers, and we particularly took I greater than 0 and I less than 0 and saw what happens. Hence, the assumption I greater than 0 leads to a contradiction. Similarly, we can show that we cannot have I less than 0. Thus, what have we concluded? The set of complex numbers cannot be ordered in such a way that above mentioned axioms which were true, which were assumed to be true in the case of real numbers are satisfied. That is the reason why the complex numbers are scattered in rather than unlike real numbers which fall in a line. Complex numbers x comma y will plot on a plane. Okay. Now, like a real number system, we can talk about arithmetic of complex numbers also. So, if a complex number z is of the form x plus iy, where x comma y are real, then x is called the real part of z and y is called the imaginary part of z. We write it as x equal to re of z and y equal to im of z. For every z equal to x plus iy, we can define its complex conjugate z bar as x minus iy and its modulus by square root of x square plus y square, and we denote the modulus of a complex number z by mod z. Thus, mod z equal to square root of x square plus y square. Some of the properties which the modulus and conjugates satisfy are as shown. Modulus of z square is z bar. Real part of z is z plus z bar by 2 and imaginary part of z is z minus z bar by 2i. Z plus w whole bar is z bar plus w bar. Modulus of zw is mod z mod w. Modulus of z is same as modulus of z bar. And modulus of z plus w the whole square equals modulus of z the whole square plus mod w the whole square plus twice real part of zw bar. Whereas modulus of z minus w the whole square equals mod z square plus mod w square minus twice real part of zw bar. The triangle inequality for complex numbers is modulus of z plus w less than or equal to mod z plus mod w, whereas modulus of z minus w greater than or equal to modulus of mod z minus mod w. Now, our main idea is we have extended real numbers to complex numbers. Now, can we extend other concepts which we studied in real analysis to complex analysis? And namely, once you have a real numbers, you can talk about real valued functions, and we can discuss about sequence of real numbers, series of real numbers, limit of a real valued function of a real variable, continuity of real valued function of real variable, differentiability, integration, etc. In fact, we can also talk about distance between any two real numbers a and b, namely if a and b are two real numbers and the distance between them is modulus of a minus b. Now, our idea is now to extend these concepts to complex functions of complex variable. So in that line, we normally the concept of continuity, limit, continuity, and differentiability is very important in case of real valued function. So here also we will try to talk about limit of a complex valued function, continuity, and differentiability of complex valued function. So in order to talk about the limit of a function, complex valued function, we need the concept of neighborhood. And once you need to talk about the concept of neighborhood, we need the notion of a metric or distance. So keeping that in mind, we define a function d from c cross c to r by d of z comma z bar equal to modulus of z minus z bar, where z and z bar are complex numbers. So when I say already we saw modulus of z can be defined, so it is possible to define modulus of z minus z bar. What are the properties modulus of z minus z bar satisfy? Modulus of z minus z bar is greater than or equal to 0. Because if you substitute z equal to x plus iy and z dash equal to x dash plus iy dash, then this turns out to be square root of x minus x dash whole square plus y minus y dash the whole square. That is a greater than or equal to 0, and it is 0 if and only if z equal to z bar. And modulus of z minus z bar is same as modulus of z bar minus z. You can take a minus 1 outside from within the modulus and use the property mod a b equal to mod a mod b, and you will get this. Also, we saw triangle inequality holds for modulus. So modulus of z minus w less than or equal to modulus of z minus z bar plus modulus of z dash minus modulus of z minus z dash plus modulus of z dash minus w, where w is a complex number. Thus, we see that d of z comma z bar defined by modulus of z minus z bar satisfies the properties of a metric. Thus, d is a metric, and we call this metric as Euclidean metric. So with this metric, the set of complex numbers forms a metric space, and it is denoted by C comma D. So we have made C into a metric space. So once C is a metric space, we can talk about open ball in C, open ball in C. So before going to that, I'll talk about extended complex plane. We know that in real numbers we have the two symbols plus infinity and minus infinity, which which are adjoined to the set of real numbers to address the question of divergence of series and sequence of real numbers, or in case even unbounded sets, etc. Similarly, now the question is, can we define complex infinity? So the set of complex numbers C can be extended by adjoining the single symbol infinity. The reason is there is no ordering in C, unlike as in R, called infinity by the method of what is called stereographic projection. I'm not going into details of the method. In this method, wherein a unit sphere x square plus y square plus z square equal to 1 in three-dimensional space, which is called Riemann sphere, is considered. And what we do is, with each point on the sphere, we associate a point on the complex plane by drawing a straight line, meeting the topmost point on the sphere and the point on the plane. It will cut the point and it will cut the sphere at a point. So we find, when you do this, we find that we can associate every point on the sphere to a particular point in the complex plane and vice versa in a one-to-one fashion. But the topmost point 0, 0, 1 cannot be associated with any point in the plane, normally called north pole. And hence we designate or we consider that point as infinity. This is the rough way of looking at projection. So thereby we include a symbol infinity to the set of complex numbers, and we extend the set of complex numbers to C union infinity. This is needed to address the limiting divergence or series or divergence sequence of complex numbers, or a limit as at infinity. Topology of the complex plane. So consider the Euclidean metric space C comma D. I define open disk as follows: delta of z naught comma epsilon is the set of all complex numbers z such that mod z minus z dot less than epsilon. This is an open disk with a center z naught and a radius epsilon. And see, when every complex number can be plotted in a on the complex plane, and so unlike real numbers, where the neighborhood in real numbers of a particular point a in real numbers in real line will be an open interval, say a minus epsilon to a plus epsilon. But in complex case, they will look like they're nothing but a disk. For example, I will show you, like here in the complex place, if you have a point z naught here, and if this will be this epsilon will be this, whereas in real line it will be some a minus epsilon, a plus epsilon. So in real line, the set of all points between to left and right of a only, but in complex plane the open ball will be as disk. This is the z minus z naught less than epsilon. And that is one one of the difference about how open balls look like in C and in R. How open ball look like in C and in R. There are many notable differences between real numbers and complex numbers, which you must know. Now, if I delete the center of that open disk, what I get is called deleted neighborhood of that center. That is, if z naught is any complex number, then the deleted neighborhood of z naught is set of all complex numbers z such that 0 less than z minus z naught modulus z minus z naught less than epsilon. And this is called deleted neighborhood because we omit the center. We make a hole at the center. Now, yes, we all know how to define open set in a case of real numbers. So in the case of complex numbers also, a subset S of C is open in C if for every Z naught in S there is a delta positive such that delta of Z naught comma delta that is an open disk around Z naught of radius delta is completely contained in S. So what does it mean? So if you have a complex, if you have a set S and I say this is open, means you for every Z naught you should be able to find a point. I mean, you should be able to find a neighborhood which is completely contained in that. Then I say it is a open. For example, it is open set. For example, you take any point on boundary, we cannot conclude it can be included in open set, because if you take any neighborhood of that point, it has points outside also inside. This is open set. Now, so we have defined a metric from on C. We having the metric in C. We have defined open balls or neighborhoods of any point complex any point in the complex plane, and then we have defined open set in the complex plane. So now now that we have defined open sets in complex numbers, we can extend the concept of limits and continuity and differentiability of real valued functions of real variables to that of complex valued functions of complex variables. Because when you talk about limit, so normally limit z tend to a, f of z equal to L means what is the meaning? Whenever z is whenever z is very close to a, right? So limit z tend to a, f of z equal to L, where f is a complex valued function, means what is the meaning? Whenever z is close to a. So what do you mean z is close to a? If a is here, means z can be close, or z can be close to in any direction it wants. This is another one difference between real and but in the case of real valued functions, if a is any point and is x is any other point close to a, it can be either close from the left or right. So whenever z is close to a, I want f of z values to be close to what a complex number L. So so this closeness can be expressed in terms of distance. The closeness can be expressed in concept of distance, and hence I can talk about a limit of a complex valued function. And if that limit happens to be the value of the function at a, then function becomes continuous. So we can talk about continuity, and also I can talk about the quotient ratio f of z minus f of a by z minus a as a derivative of f at a as limit z go to a. So these open sets are very helpful in defining this limit concept, continuity, and differentiability. A non-empty connected subset of C is called a region. So by a region of a complex plane, we mean a non-empty connected subset. And in fact, I think it's non-empty open connected subsets. I'm sorry, there's missing. This will be open. I have missed the word open. Non-empty open connected subset of C is called a region. Now, a sequence in complex plane. We know, we have studied in real analysis the sequence of real numbers, series of real numbers, convergence, divergence, etc. So the same concept can be extended to complex numbers also, meaning we can define sequence of complex numbers and series of complex numbers. So by a sequence of complex numbers, we mean a function from the set of natural numbers n to the complex numbers, and it is denoted by zn. That is, these are f values. F of 1, f of 2, f of 3 are all complex numbers. So I denote them by z1, z2, z3, etc. Similarly, by a series in of complex numbers, we mean a pair zn n equal to 1 infinity and sn n equal to 1 infinity, where zn is a sequence of complex numbers and sn's are the partial sums, z1 plus z2 plus zn for each n1 equal 1 and n equal to 1 to the 50. The convergence and divergence of sequence of complex numbers is defined in a similar way to that of real numbers. Coming to functions of complex functions in the either real valued complex valued function, first of all, let us recall the definition of a function. A function f from a non-empty set A into another non-empty set B is a rule which associates with each element in a unique element in B, and we denote it by f from A to B. So when A and B are either the set of real numbers or complex numbers, there are four main classes of functions, namely real valued functions of real variable, that is set of all f from R to R or any subset of R to R. Real valued functions of a complex variable, so the range is real valued, so f from C to R. Complex valued functions of a complex variable, that is set of all functions of a real variable. Complex valued functions of the real variable, that is f from R to C. and complex valued functions of a complex variable, meaning f from C to C. So generally, we need not take the whole set as domain. In fact, more generally, from subsets of respective domains, we can define functions. Now, among these four types of functions, real valued functions of real variables were you would have studied very well about them in your real analysis course. You would have done continuity, limit, etc. from an interval a comma b to r, differentiation, integration, everything. So we are not interested in studying about those functions in complex analysis course. But and if you look at the complex valued functions of a real variable, if you look at that is the third one. Complex values functions of that is for every x, f of x is a complex number. Every x real, f of x is a complex number, meaning it's a pair of two real numbers. Say u1 comma v1, u1 comma v1. So again, you can treat functions from real number to complex numbers as a pair of real valued functions. So which is also is same as studying functions from real numbers to real numbers. So the interesting functions are complex valued functions of complex variable. Complex valued functions of complex variable, that is the last one, f from C to C, are really interested in to study. And if f is a function from C to C, we denote f by f of z equal to u of x comma y plus I v of x comma y, because f is a complex valued function, so the image will be a complex number. So it depends on z, where z is, say if z is x plus I y, z depends on x and y. Therefore, u depends on x and y, and v depends on x and y. So we denote a complex valued function f by f of z equal to u of x comma y plus I v of x comma y, or in short u plus iv. Thus, what do you find here? U of x comma y is a real number. V of x comma y is a real number. Thus, u and v are functions from R2 to R. U and v are functions, real valued functions from R2 to R. We are now ready to define limit of a complex valued function of a complex variable. In fact, we define the similar way as we define a limit of a function of a real variable, real valued function of a real variable. Let f be a complex valued function of a complex variable defined in a deleted neighborhood of point A. We say that f of z has a limit L as z approaches A. If given epsilon positive, there exists a delta positive such that whenever 0 less than z minus a less than delta, that is, we are considering the deleted neighborhood of A, we have f of z minus L less than epsilon. And we write this as limit z tend to A, f of z equal to L. Not that here A and L are complex numbers. So let me graphically picturize this. So now, what is it? So if you have limit z tend to A, f of z equal to L means, so here is your A, here is your L, and let us also look at the limit the different. Suppose this is say m, where m is real number A. Okay, so in this case, if A is any point, and here say A minus delta, A plus delta, and here will be m. This will be m. So here you see that when I say limit x, in the case of real valued functions, when I say x is approaching A, so then x is either to the left or right of A. X can be either to the left or right of A. So for this limit to exist, you know pretty well that right hand limit and left hand limit and right hand limit must exist and should be equal. So we talk about left hand limit of real valued function of real variables, right hand limit of real valued function of real variables, and then for the limit to exist, we should have both the limit to exist. But in the case of complex variable or a complex valued function of a complex variable, when I say z approaches A, there are infinite number of directions for z to be close to A. That means you can find a disk about A, there are z points close to A in every direction. So in every direction, the limit should exist. In every, no matter which direction z approaches A, in every direction, this limit should exist. Not only that, it must be equal to L. That is in this case. That is f of x, that is, you draw a ball with center L and some radius epsilon, then f of z should be in that ball. Whenever z is in this ball with center A and say radius delta, my f of z should be in this ball. F of z should be very close to L by a distance of less than epsilon. This is what what I stress is the difference of real value limit in case of real valued functions and the limit in case of complex valued functions. So in the case of real valued function, there are only two different limits, right hand limit and left hand limit. But here we have, because there are only two paths for x to approach A, but here there are infinite number of paths for z to approach A. So for the existence of the limit, the limit should exist in first of all, limit should exist in no matter which path you come to A, and it should be equal in every path. Similarly, when you go for continuity, before that, some remarks. In the case limit z, whatever I mentioned geometrically, I am writing here. In the case limit z tend to A, f of z equal to L, there are infinitely many directions from which the point z can approach the point A. Unlike their real counterpart, limit x tend to be f of x, where there are only two possible directions, namely x can approach either b from either left or right. Thus, in complex case, limit z tend to f of z exists and equals L if and only if limit exists in all possible directions and equals n in each direction. Similar to limit of real value, two real valued functions of real variable, you have certain properties of limit for complex valued functions of complex variable. So if f and g are two complex valued functions of a complex variable, and if a is any complex number, then the following are true. Limit z tend to a f of z plus g of z is same as limit z tend to a f of z plus limit z tend to a g of z. Limit z tend to a f of z minus g of z is same as limit z tend to a f of z minus limit z tend to a g of z. And limit z tend to a f of z into g of z is same as limit z tend to a f of z into g of z. If limit z tend to a g of z is not equal to 0, then limit z tend to a f of z by g of z equals limit z tend to a f of z by limit z tend to a g of z. So these are properties similar to their real counterpart. But here we have some extra limit because z and L being complex numbers, or L f of z being complex, and we can talk about the following limits also. Limit z tend to f of z bar is same as, if limit z tend to f of z equal to L, then limit z tend to f of z whole bar is L bar. Limit z tend to real part of f of z is real part of L. Limit z tend to imaginary part of f of z is imaginary part of L. Limit z tend to modulus of f of z is same as modulus of L, and limit z tend to 1 by f of z equal to 1 by L, provided L not equal to 0. So before going to main concepts of complex valued function, we must know the limit properties also. Continuity of a complex valued function of complex variable. You all know what is continuity of a real valued function. So let me first recall in case of real valued functions, right? Suppose f is a function from some subset A of R to R, right? And A is a point in A. Here, please note that A is a point in A. I say f is continuous. F is continuous at A if limit extending to A f of x equal to f of x. In case of limit, okay, in case of real valued function of a real value. So it is mandatory that A should be in the domain of A, small a, f. A should be in the domain of f. Otherwise, f small f will not assume A. So, I mean, it will not take value of at A. It will not take value at A. Unlike, but in the limit case, L need not, here when you define the limit of a function in general, L need not be in domain of A. Need not be in domain of f. L need not be in the domain of f. Whereas here, it is mandatory that A should be in domain of f and the limit should equal f of A. Then I say f is continuous. So this is the case of real. Similarly, in the case of complex valued functions also, in the case of complex valued functions also, we can define, suppose f of z is a complex valued function defined in an open disk around A. So open disk around A. then we say that f of z is continuous at a if limit z and a f of z equal to a. What does it mean? Given epsilon positive, I can find a delta positive such that modulus of f of z minus f of a less than epsilon whenever mod z minus a less than delta. So let me see. Okay. Yeah, see here. Replace L by f of a in the definition of continuity. Replace L by f of a in the definition of continuity. And but there is one difference here. I demand a to be in the domain of f, so the neighbor you consider cannot be deleted neighborhood. I'll explain again. Here 0 less than mod z, in the case of general limit z approaches a, if given epsilon there is a delta such that 0 less than mod z minus a less than delta, that is z cannot equal a because a need not be the domain of a. But here in the case of continuity of a function, a is very much in the domain of a, and z is also in the domain of a, so z can be equal to a. So we cannot consider deleted neighborhood, we have to consider usual neighborhood of a. Some remarks: as in the case of real numbers, the sum, difference, product, and two continuous functions at a point a are again continuous, and whenever the quotient of two functions are defined, the quotient is also continuous. By whenever, what I mean by quotient is defined, the denominator should be non-zero at a. The denominator function should be non-zero at a. Only then we can talk about quotient of continuity of quotients of two continuous functions. If f of z is continuous at a, then it should be small z. Real part of f of z, imaginary part of f of z, and modulus of f of z are also continuous at a. It's because it's natural, because if you take f of z, if you write it as u plus iv, if I can write it as real part of f of z plus I times imaginary part of f of z. So if you talk about continuity of f at a, right? If f is continuous at a, then naturally this should be continuous at a, and this should be continuous at a. This is what the result tells. And modulus. Remember, modulus of a complex valued function is a real number, real number. So that also should be continuous at a. Now, what can you tell about the concept of continuity? The concept of continuity is a local character. In the sense, it is restricted to the point at which you are talking about continuity. That is, if f is a map from some domain of the complex plane, say D, with complex values, then f is defined to be continuous in D if f is continuous at every point in D. So, earlier we saw what is continuity of a function at a point. Now I am interested in continuity of a function, a complex value function, in a set or a domain. So domain is consists of points in the complex, some points in the complex plane. So I say f is continuous in the domain D if it is continuous at every point in D. Since both the concept of limit and continuity, we need the values of the function in a disk around the point. The definition of continuity in a domain is non-trivial only if around each point there is an open disk around that point which is completely contained in D. That is, domain is open. What do you mean by that? See, in order to define continuity of a function, we expected. I mean, what was 1 minute? Continuity. When you talk about continuity, limit z tend to a, f of z happen to be f of a. That means whenever z minus a is close to 0, my f of z should be close to f of a. Or whenever z is close to a, f of z should be very close to f of a. So f of a, if I want to talk about f of a should be very well inside the domain of f. A should be very well inside the domain of f. So only then f of a will come in the range of f. Okay, that means what? Whenever you, what is the meaning of this? Technically, I'll write the definition. For every epsilon positive, I can there exists a delta positive such that modulus of f of z minus f of a less than epsilon whenever modulus of z minus a less than delta. So what does it mean here? It means that your f of z should be in the ball with f of a and a radius epsilon whenever z is in the ball with a radius gender a and radius delta. So given any, I mean, how can you guarantee f of z is in a ball? So you recall the concept of open set. If I have an open set, what when do I say a set is open? If you take any point in that, you should draw a neighborhood such that that point is contained. That neighborhood is contained in that set. So here, with f of a as sender, you draw a open ball. Draw a open ball with some radius epsilon. And when I say f of z is inside that, it means that is f is in the what I can f of z is in the range of f. F of z is in the range of f. Okay, that is f takes is a I can tell f of z is in the range of f. So that tells that f of a is open because points near to f of a are also of the form f of z. That is, there are also image of some z in the disk delta of z comma delta. For such z only, the image lies inside this disk. Right? That tells that this is open. That is what we demand, that the domain should be open because it follows from the fact that whenever f of z is f of a is the center of the disk, f of z also lies inside that disk. Next, we talk about differentiable function. A complex valued function f defined in a non-empty set D is said to be differentiable or complex differentiable at A if the limit z and a f of z minus f of a by z minus a equals, which also equals limit h tend to 0 f of a plus h minus f of a by h exist. If this limit exists, I say f is differentiable at a. And in this case, we denote the limit by f dash of a, and it is called the derivative of f at a. And generally, f dash of a is also a complex number. So we write f dash of a equal to limit z and a f of z minus f of a by z minus. This also looks very much familiar to that ordinary the derivative of a real valued function at real valued function. Some results about derivative. A real valued function of a complex variable either has derivative 0 or derivative does not exist. See, I am talking about real valued function of a complex variable, like real part, is that going to real part of z, imaginary part of z, or modulus of z. These functions, either they do not have derivative or derivative becomes 0 if at all they exist. If f has a derivative at a, then it is continuous at a. This result also is there is an analog of this result in real valued case also. Whenever you have a real valued function differentiable at a point a, then it is also continuous at that point. So same result extends to complex valued functions also. And the algebra of differentiable functions, if f and g are differentiable at a, then their sum f plus g, difference f minus g, product f into g, and the quotient f by g whenever g of a not equal to 0, and the scalar multiple cf are also differentiable at a. And thus we have f plus g dash of a equals f of a I'm sorry, there is f of a f dash of a plus g dash of a, f minus g whole dash at a is f dash of a minus g dash of a, f into g whole dash of a equal to f dash of a g of a plus f of a g dash of a. Well, there is a mistake in this fourth point. Please excuse me. I'm sorry. It should be quotient rule. It should be quotient rule. G of a the whole square, and that's why we assume g of a not equal to 0. I seek your apology. I seek your excuse. Sorry. So here there is a mistake. This quotient rule should come, and CF whole dash at A should be CF dash at A. The functions real part of z, imaginary part of z, mod z, z bar, and argument of z are nowhere differentiable in C. You cannot find derivative. The derivative of these functions that will not exist at any point in C. Any point in C. Now we come to the last concept, analytic function. The analytic functions. A function f is said to be analytic or holomorphic at a point A if it is differentiable at every point in some neighborhood of A. It is differentiable at every point in some neighborhood of A. So this is more stronger than differentiability. So we demand not only differentiability at a point A, but also at every point in some neighborhood of A. So what does it mean? So when do you say function is analytic? So you have some domain here, the image domain. So this is suppose omega. We have op of omega, and here you find A, right? And I say f is differentiable analytic at A. Okay, f is analytic at A if first point f dash at A exists. Number two, there is a neighborhood of A such that f is differentiable at every point in A, at every point in the neighborhood of A. So we not only demand differentiability at A, but also at neighboring points of A. In that say, then I say f is the analytic at A, analytic at A. Now a function f is analytic in an arbitrary set S if it is differentiable at every point in some open set containing S. See, when I say arbitrary set is, S need not be open. But normally we talk about differentiability in open set only because of the limit concept. So a function f is analytic in an arbitrary set S if it is differentiable at every point of some open set containing S. Some open set containing S. Only then you can talk about the neighborhoods of the point where you take the limit. Now, some examples of, and there are so many examples, I have quoted some examples here. Z is analytic at every point in the complex plane. Similarly, Z square, sine Z. Look at the function 1 by Z. It is analytic at every point in the complex plane except at Z equal to 0. Because at Z equal to 0, the function itself is not there. We can keep on giving several examples. Due to time, I don't know how much time I have, so I stopped with these examples. Now, if at all you have a function, complex valued function of a complex variable, which is analytic at every point in the complex plane, then I call that function as an entire function. So, an entire function is one which is analytic in the whole complex plane. Best examples are polynomials in Z, sine Z, cos Z, e power Z, or their product in this e power Z, cos Z, Z power 5 cos Z, etc. These are all examples of entire functions. Now, I stop with two main results of analytic functions, especially if f equal to u plus iv or u of x comma y plus iv is analytic in a domain D, then u and v necessarily satisfy dou u by dou x equal to dou u by dou y and dou u by dou y equal to minus dou v by dou x. These are called Cauchy-Riemann equations. They are essentially partial differential equations if u and v are unknowns, or otherwise it is about to satisfying. These are called Cauchy-Riemann equations. So if an analytic function should necessarily, the real and imaginary part of an analytic function should necessarily satisfy Cauchy-Riemann equation. Further, real and imaginary part of an analytic function are harmonic. That is, if u f of z equal to u plus iv is analytic in D, then u and v are harmonic. That is, dou square u by dou x square plus dou square u by dou y square is 0. So is 0. Similarly, dou square u by dou x square plus dou square u by dou y square equal to 0. Now, one important property of an analytic function is that if a function is analytic, that means derivative exists, then it is differentiable any number of times. It is differentiable any number of times. If f dash exists, then higher order derivatives also of analytic function at that point exist. Therefore, this tells that f can be, if at all f is analytic at a point A, then it can be expanded as a power series in A. It can be expanded as a power series in A for any power series in Z minus A for point Z very close to A. And there is a name for, we call this as Taylor series expansion. Even in real valued case, we have Taylor series expansion. So this I stop. The references are complex analysis by V. Karnagaran, foundations of complex analysis by S. Ponusamy, and mathematical analysis Tom Foster. So I stop here. Any questions? Any question?
Thank you so much, sir, for spending your valuable time for us. Now we'll move on to question and answer session. If you have any questions or queries, kindly post in the chat box. Uh, I think there are two questions, sir.
Yeah, very much. Let me take it.
So, is there any way to see function from complex plane to complex plane? For example, entire function like sin x, and as real function sin x since it is for dimension.
Pardon? I didn't understand the question. 1 minute. 1 minute.
Yeah, sure.
Can you repeat the question?
Is there any way to see function from complex plane to complex plane? For example, entire function like sin z
Hmm.
as real function sin x since it is four dimension. Any application is very useful to have asked, sir.
1 minute. Is there any way to see function from complex plane? That's what. Yes. Sin z is from C to C. E power z polynomials. All entire functions are different from C to C only. As a real function, yeah, because see, sin x is not from R to R. Its domain is range is -1 to 1, -1 to 1, but it is four dimension. Uh, Not understanding. Okay. Why multivalued functions like a log is that allowed in complex analysis but not in real analysis case as it breaks
As it
function
breaks
to real.
functions.
Hmm. See, in complex analysis, we define. Say, actually, okay. What happens is, what is actually multivalued function is, they take several values. So what we can do is we can restrict their domain or their domain. I mean, we can to see, for example, if you take a multivalued function of log z, it will be we what we have there. We have something called log branches of the logarithm branches, right? Now what we can do is we need not look at the function at all branches. We can it's enough to consider only those branches where the function is analytic and study the function in that branch. But in case of real analysis, we don't have such things. We don't have branches. That's what I feel.
Okay. Thank you, sir, for answering patiently. Shall we move on to vote of thanks, sir?
To me, hello. Any other questions?
I think there are no more questions, sir. Yes, sir, there are no more questions. Shall we move on to vote of thanks, sir?
Yes. 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 Yes.
Now I request Dr. K. Priyadarshini, Assistant Professor, Department of Mathematics with Computer Applications, to give over the vote of thanks.
It gives me immense pleasure to thank our speaker, Dr. S. Sunil Verma, Assistant Professor, Department of Mathematics, Madras Christian College, on behalf of Department of Mathematics with Computer Applications. I thank our resource person for his informative speech and a complete introduction about complex analysis. I express my sincere gratitude to our secretary, Sri Ashok Kumar Mundraji, and our principal, Dr. S. Sandosh Babu, and our head of the department, Mrs. B. Sangeeta, for their constant support in organizing webinar series. I will fail in my duty if I don't thank our faculty members and our participants. Thank you all for your support.
அவ்வளோதானே மேம், க்ளோஸ் பண்ணிடலாமா?
சார் ஃபீட்பேக் லிங்க்
ஃபீட்பேக் லிங்க் போடுங்க. யார்கிட்ட இருக்கும்? நான் குரூப்ல போட்டிருக்கேன்.
நான் எடுத்து போடவா சார்? ஆக்சுவலி
போடுங்க.
இந்த ஸ்க்ரீன் இருக்கு, இந்த பிபிடி இருக்கு.
சரி, நான் எடுத்து போட்டுமா? ஓகே, நான் போடுறேன்.
நீங்க எடுத்து போட்டுருங்க. ஏன்னா இந்த பிபிடி இதுவாயிருக்குல்ல, ஓப்பன்ல இருக்கு. நான் ஸ்க்ரீனுக்கே வர முடியல. சார் லீவ் ஆயிட்டாரா?
அவர் லீவ் ஆயிட்டார் மேம், ஒரு லீவ் ஆயிட்டார்.
சரிங்க சார். நீங்க வந்து
ம்.
க்ளோஸ் பண்ணதுக்கு முன்னாடி ஃபீட்பேக் லிங்க் போட்டுட்டு க்ளோஸ் பண்ணிடுங்க சார்.
சரிங்க.
சார் ப்ராட்காஸ்ட் நிறுத்திட்டீங்களா?
இல்ல மேம், போயிட்டு இருக்குது. நிறுத்திடவா?
ஆமாம்
இல்ல,
சார்.
ஃபீட்பேக் லிங்க் போட்டு தானே நிறுத்தணும்.
சரி, போட்டு நிறுத்திடுங்க சார்.
ஓகே. எதுல மேம் போடுறது? பிரைவேட்ல நமக்கு போடுவாங்களா, இல்ல அதுல நம்ம யூடியூப் சேட்ல போடணுமா?
கமெண்ட்ஸ்ல போடுங்க சார், கமெண்ட்ஸ்ல.
கமெண்ட்ஸ்லயா? ஓகே, ஓகே.
யாராவது செக் பண்ண சொல்லுங்க சார். நானே செக் பண்றேன்.
அதான் போறேன்.
சார் என்ன ஸ்க்ரீன்ல ரிமூவ் பண்ணிடுங்க.
ஓகே. ஹலோ, சொல்ல. ஹலோ மேம், அது லிங்க் வர
சார் ஃபீட்பேக் போட்டாச்சு இல்லை சார் ஃபீட்பேக் லிங்க்கு?
மேம் வாய்ஸ் கேக்குதுங்களா சுப்லட்சுமி?
கேக்குது சார்.
ஒன்றும் இல்லை மேம், என்னால் ப்ரைவேட் சேட்டில் தான் போட முடியுது, பப்ளிக் சேட்டில் போட முடியல. லிங்கை போட்டால் லிங்காக காப்பி ஆக மாட்டேங்குது, டெக்ஸ்டாக தான் காப்பி ஆகுது.
ஒன் செகண்ட் நான் போட ட்ரை பண்ணுறேன் சார்.
ஓகே மேம்.
எனக்கு வரலையே. I think they can copy this and open the link.
இல்ல இங்க இந்த லிங்க் வந்து ஓபன் பண்ணவே, அதான் போட்டா லிங்கா வர மாட்டேங்குது, டெக்ஸ்டா தான் வருது.
I think they can copy.
சரி ஓகே மேம். ஓகே. இல்ல இங்க லிங்க் வந்து ஓபன் பண்ணவே, அதான் போட்டா லிங்கா வர மாட்டேங்குது, டெக்ஸ்டா தான் வருது.
சார் வருது.
I think they can copy. சரி ஓகே மேம். ஓகே மேம், க்ளோஸ் பண்ணிட்டுமா? என் கார்டு கஸ்டமர்.